All right, so now let's get into preparation of aldehyde and ketones. These are actually all reactions that we've learned about before. So I just want to make a note of these slides. You can find where in your textbook or where in the posted lecture slides we first discussed these reactions up in that top corner there. Okay, so the first one is starting out. So if we're talking about, now we're going to talk about aldehyde preparation. There's a lot of overlap. The biggest difference is usually whether or not it's on the end. Okay, so remember for primary alcohols, where that alcohol group is at the end of an alkyl chain, we can use a weak oxidizer that will oxidize to an aldehyde, right? Remember, if we used a strong oxidizer in this case, we'd actually get a carboxylic acid. So we're going to have to use a weak oxidizer here. The most popular one is PCC. Okay, and I know that there's like a lot written in this little box here, it can kind of make your eyes cross. So let's just go through and make sure we know what the key players are. PCC is the most popular aldehyde oxidation technique that is commonly used. Okay, we actually learned about 3 though. And then notice over here, this is just this solvent that's used, dichloromethane. Another method is DMP. I believe the claim of fame of DMP was that it's more green or cheaper to dispose of than PCC is. And again, we just have this solvent. So I guess what I'm coloring here is kind of the meat of what's really important. You know, for full credit, you would have to, you know, you could include these solvents. Actually, for PCC and DMP, I don't really care if you put the fact that dichloromethane is there or not. The PCC is the really important one, right? Or the DMP, that's the part that if you don't have that in your reagent list, you're going to get in trouble. As well as this guy right here. This is the Swern oxidizer. Again, my solvent DMSO. This is really important that you have that second step though with triethylamine, okay? But you would get a whole lot of partial credit if you just had included that. Okay, but just note that all 3 of these are going to accomplish the same goal. They're all weak oxidizers, which will turn a primary alcohol into an aldehyde. We also know how to make aldehydes from alkenes. If you have an alkene where there are 2 hydrogens on either side, then you can use the ozonolysis, which remember just cleaves right down the middle and replaces either side with an oxygen, right? So I guess just to color code here, who's going to who? This would be 1/2 of the molecule. This would be another half. If your real goal is to prepare an alkene, or I'm sorry, to prepare an aldehyde, you probably want to use a symmetric one, right? If the orange R and the blue R are different groups, I'm just going to have to figure out how to separate those compounds in the mixture after I do my ozonolysis. So if your goal was to prepare aldehydes, you'd probably want to start out with a symmetric one. We also know how to make aldehydes from alkynes, right? From triple bonds. Importantly, they have to be terminal alkynes, right? And that would be using, this would be the meat of this reaction here. This is a hydroboronation reaction. Honestly, if you just said BH3, I would also give it to you. We learned about why using this R2BH is a little bit better in section 9.7, but whatever. Point being is that you remember that it's the hydroboronation of an alkyne that gives you the aldehyde, okay? Remember, what are these hydroboronations doing for you? They're creating the anti-Markovnikov addition where you have addition onto the less highly substituted group. And what really happens in these reactions, if you remember, is that first you put an alcohol group or a hydroxy group on that terminal carbon, but then this is called an enol, which will tautomerize into an aldehyde, right? These enol, we actually call it an enol keto tautomerization. But if you're using a terminal alkyne, it's an aldehyde. But yeah, so this would have also been in this section too. You can sort of go back and remind yourself that you, very simply, similar to what BH3 does to an alkene, you put a OH group on that less highly substituted carbon, but then because you create an enol, it's going to tautomerize to this aldehyde. Okay, so now in terms of ketones, how do we use that? We can oxidize a secondary alcohol to a ketone, and we don't really have to worry about how strong our oxidation is. So we can use something, bust out the big guns like this chromium, right? Anytime you see chromium, you think oxidation. Any of those other ones would have worked as well. So PCC would also work. You just have to oxidize that secondary alcohol to a ketone. Okay, so any sort of oxidation technique would work. We could do the same if we had an alkene that was substituted on all 4 carbons. Was substituted on all 4 positions. Then when we did the ozonolysis reaction, we would create a ketone at the end of the day instead of an aldehyde. So again, you need a tetrasubstituted alkene for this, but those are just these ozonolysis reactions of alkenes. And now we have a similar to what we saw before with the aldehydes, where we can turn, it actually doesn't even have to be terminal, but where we can turn an alkyne into a ketone. And this is using H2SO4, water, and this mercury sulfate compound. Remember, what this is going to do is basically this counter of what the hydroboronation does. It's going to add an OH group to the more highly substituted carbon. So in this first step, what you would create is this compound right here, but this is again an enol. So it's going to tautomerize into a ketone. So this is again that keto-enol tautomerization. So that's another way that you can prepare a ketone. And then the last one is one we just learned about last chapter, which is these Friedel-Crafts acylation reactions, where you start out with an acyl halide and acyl chloride, and then you do a an electrophilic aromatic substitution reaction. It creates a very specific type of ketone where one side is a benzene ring. We call that an aryl ketone.